Okay, so now let's continue. So let's say we have two messages and the size of my, say, the error detection code is fixed to be, say, 2 bits. Okay, the messages could be of any size, but let's say the size of my error detection code is fixed to be 2 bits. So for, say, the message M1, my error detection code value, again, if you have only 2 bits, the value of the error detection code could be what? Either 0 0, or it could be 0 1, or it could be 1 0, or it could be 1 1. These are the 4 possible values. So let's say the error detection code for M1 comes out to be 0 0. For M2, the error detection code could be one of these 4 values. Similarly, if the error detection code for M1 is 0 1, again for M2 it could be one of these 4. And similarly, if it is 1 0 and so on, again one of these 4. So we have 16 possibilities, right? If it is 0 0 for M1, it's going to be one of these 4. Again 0 1, the same 4. 1 0, one of these 4. So out of these 16 possibilities, there are only 4 scenarios where the two messages have the same error detection code. When does that happen? So something like this. The two messages have the same error detection code, and here it is 0 1 for M1, 0 1 for M2. Similarly, you have 1 0 for M1 and 1 0 for M2, and you have 1 1 for M1 and 1 1 for M2. So out of the 16 possibilities, there are only 4 possibilities where the two messages have the same error detection code. So the probability that M1 and M2 have the same error detection code is going to be what? 4 out of 16. Now again, M1 and M2 should not be the same, right? Because if M1 and M2 are the same, then there's no need to do this analysis. They should have the same error detection code. So we need to have this kind of assumption that they don't have the same error detection code. I'm looking for the not equal to symbol. Alright, let's just let's see if I find it here. Okay, it's here. So M1 not equal to M2, okay, has the same error detection code is going to be the probability that M1 and M2 where M1 not equal to M2 has the same error detection code is going to be 4 over 16, which is 1 over 4. Okay, so which means, you know, again from probability, the probability that M1 not equal to M2 have a different error detection code is going to be 1 minus of 1 over 4, which is going to be 3/4. Right, so that's the probability that two different messages have a different error detection code. And we could extend this analysis further, right, and say that if we use, so this 1 over 4 is basically from 1 over 2 square, where this 2 square is basically like this, right? This 2 corresponds to the size of the error detection code. Alright, so if we use for a k-bit error detection code, the probability that the two messages M1 again not equal to M2 have the same error detection code is going to be 1/2 raised to k. All right. So that means have different error detection code is going to be 1 minus of 1/2 raised to k. So the probability that m1 not equal to m2, the two different messages have a different error detection code, is going to be 1 minus of this 1/2 raised to k. Alright, so if we have something like this, so if we extend this analysis to something like this, where we have k and 1/2 raised to k and 1 minus 1/2 raised to k, okay, so let's do the math. Okay, so if you have 1, so it's going to be 1/2, and that's going to be, this is going to be also 1/2. If you have 2, this is going to be 1/4. This is going to be 3/4, and if it's going to be 3, it's going to be 1/8. What's this? This is going to be 7/8. And if it's going to be 4, this is 1/16. This is going to be 15/16, right? And if it's 5, this is 1/32. This is 31/32, and so on. So which is larger? As you increase the size of the error detection code, if the two messages are different, m1 not equal to m2, the probability that they have a different error detection code, which is given by this expression, is this. So if I use an error detection code that is 5 bits long, the probability that two different messages have a different error detection code, this is what we prefer. If the two messages are not the same, if m1 is not equal to m2, we prefer them. We want them to have two different error detection code. We don't want two different messages to have the same error detection code, because then if m1 changes to m2, then we could not detect the error if both m1 and m2 end up having the same error detection code. We want to be able to detect the error if m1 changes to m2. Right, during transmission, even one bit changes, then the two messages are different. So if m1 changes to m2, we want them to have a different error detection code. Alright, so the probability that two different messages have a same error detection code is 1/2 raised to k. If you use k bits for the error detection code, then the probability that they have a different error detection code, if they are different messages, then it's given by this. So if we use k bit or 5 bits, for example, then the probability that two different messages have a different error detection code is 31/32, which comes out to be 96%, 96.8%. So if we even increase this further, say for example 6 bits, right, it is 1/64, which is 63/64. That comes out to be 98.4. If you know the standard hashing algorithms that we use for message integrity, say even 32 bits or 16 bits, let's say we start with 16 bits, then it's going to be what, 1/2, you can say like this, but it's actually 1/2 to the 16 because 1 is, the numerator is just 1, but we could put something like this. So this is going to be what is 2 to the power 16 is going to be something like this, minus 1. So that's really going to be 99.99%, right? So this is the probability that the message is not going to be the error detection code is not going to be the same for two different messages. Then you can keep increasing, right, the error detection, the size. Then you'll see how good it turns out to be. We want this to be as close as 1, and that we already got it as close as 1 when we use 16 bits for the error detection code. Now this is what 16 bits is used for checksum, but if you go for SHA and more powerful integrity algorithms for hashing, they can go up to 128 or even 256 bits. Then you can imagine how powerful they are. If you even change 1 bit in the message, then the two messages should have a different error detection code or a hash value. That's what it is. Okay, so the error detection code is also called the hash value because they represent the message. If even 1 bit changes the message, then the hash value should change, right? So we'll stop with this.